You're standing on an island that didn't exist 5 years ago, beneath your feet. There's no bedrock, no solid ground, just soft marine clay and loose sand stretching down 30 meters. Above you, a gleaming airport terminal spans over 1 million square meters, handling 50 million passengers a year. And somehow, despite sitting on reclaimed land in the middle of the Persian Gulf, despite the weight of runways and terminals and taxiways pressing down on unstable seabed, the entire structure isn't sinking, not even a little. This is the new Hamad International Airport expansion in Qatar, and it represents one of the most audacious engineering gambles in modern construction. Because here's the thing, airports are heavy. A single Boeing 777 weighs over 350 tons fully loaded. Multiply that by hundreds of aircraft. Add the terminals, the parking structures, the fuel depots, the cargo facilities, and you're looking at millions of tons of dead weight pressing down on land that was underwater just years ago. The math is brutal. Reclaimed land settles, it compresses, it shifts, and if you build an airport on it without solving the sinking problem first, you don't get runways, you get disaster. Planes can't land on pavement that's cracking and subsiding. Terminals can't function when floors are tilting and walls are splitting. So how did Qatar build an airport on the ocean without it sinking into the seabed? The answer involves giant stone columns driven deep into the earth, millions of tons of sand dredged from the seafloor, and construction techniques that sound insane until you realize they're the only thing keeping the whole project from collapsing into the Gulf. Let's break down the full process, from the first survey of the seabed to the moment the first plane touched down on reclaimed land, and see exactly how you build an airport on the ocean without it sinking. Before we talk about solutions, we need to understand the geology. The Persian Gulf near Doha isn't like building on granite or limestone. The seabed consists of layers of soft marine clay, loose sand, and silt, materials with almost no bearing capacity. If you tried to place a heavy structure directly on top, it would sink like a stone dropped in mud. Engineers conducted extensive geotechnical surveys before construction began. They drilled core samples from the seabed, analyzing soil composition, moisture content, compressibility, and shear strength. The results confirmed what they already suspected. The natural ground couldn't support an airport, not even close. Here's the specific problem. When you place weight on soft soil, the soil compresses. Water trapped between soil particles gets squeezed out, and the ground settles. This process, called consolidation, can take years or even decades, and it doesn't happen evenly. Some areas settle more than others, creating differential settlement, the nightmare scenario where one part of a runway drops while another stays level, turning smooth pavement into a roller coaster. So the engineers faced a fundamental question. How do you build an airport on ground that can't hold weight? The answer came in two parts. First, create new land that's better than the seabed. Second, reinforce that land so deeply and thoroughly that it can handle the crushing weight of an international airport. The first step was land reclamation, the process of creating new land where there was once only water. This isn't new technology. Dubai, Singapore, Hong Kong, and the Netherlands have all reclaimed massive areas from the sea. But doing it for an airport adds unique challenges because airports demand flat, stable, precise graded surfaces. The process began with dredging. Massive dredging vessels sailed into the Persian Gulf and began sucking sand and sediment from the seafloor. These aren't small boats. They're floating factories equipped with powerful pumps capable of moving millions of cubic meters of material. The dredged sand was pumped through pipelines and deposited onto the construction site, gradually building up layers of new land above the waterline. But you can't just dump sand randomly and call it a runway. The material had to be carefully placed, graded, and compacted in controlled layers. Engineers used GPS-guided equipment to ensure the reclaimed land was built to precise elevations. Too low, and you risk flooding during high tides or storm surges. Too high, and you waste material and create drainage problems. Every square meter had to meet exact specifications. Over months, the new land took shape. What was once open water became a massive artificial island, large enough to accommodate runways over 4,000 meters long, terminal buildings, taxiways, and all the supporting infrastructure an international airport requires. But creating land is only half the battle. Freshly placed sand is loose and unstable. If you tried to build on it immediately, the weight of the structures would compress the sand, causing settlement. You'd end up with cracked pavement, tilting buildings, and structural failure.
To prevent this, engineers used a process called dynamic compaction. Here's how it works. A massive weight, often a steel or concrete block weighing 10 to 20 tons, is lifted by a crane to a height of 20 to 30 meters, then dropped onto the ground. The impact sends shock waves deep into the soil, forcing sand particles closer together and squeezing out trapped water and air. This process is repeated hundreds of times across the entire site, in a grid pattern that ensures even compaction. After each drop, engineers measure the ground's density and settlement. When the ground stops compressing significantly, it means the soil has reached maximum density and can support heavy loads. Dynamic compaction is loud, violent, and slow, but it's also incredibly effective. By pre-compressing the fill material, engineers eliminate most of the settlement that would otherwise occur after construction. The ground becomes stable enough to support structures without sinking dangerously, even after compaction. The underlying seabed, the original soft clay and silt beneath the reclaimed sand, remained a problem. That layer couldn't be removed or replaced. It was too deep, too extensive, so engineers had to improve it in place. The solution was stone columns, also called vibro replacement or aggregate piers. Here's the concept. You drill or vibrate a probe deep into the soft soil, creating a vertical hole. Then you fill that hole with crushed stone, compacting it in layers as you go. The result is a column of densely packed gravel extending from the surface down through the weak soil into more stable layers below. These stone columns serve multiple functions. First, they act as vertical reinforcements, transferring the weight of the airport down through the soft soil to firmer ground. Second, they accelerate drainage. Water trapped in the clay can escape through the permeable stone, speeding up consolidation and reducing long-term settlement. Third, they increase the overall stiffness of the ground, preventing differential settlement. In the Hamad International Airport expansion, thousands of stone columns were installed across the site. Each column was typically 0.8 to 1.2 meters in diameter and extended 15 to 30 meters deep, depending on soil conditions. The columns were spaced in a grid pattern, with closer spacing in areas that would bear the heaviest loads under runways, terminal buildings, and parking structures. Installing thousands of stone columns is a massive undertaking. Specialized equipment called vibroflots or depth vibrators is used to penetrate the soil and compact the stone. The process is methodical and time-consuming, but it's the foundation, literally, of the entire project. Stone columns work well for distributed loads like runways and taxiways, where weight is spread over large areas. But terminal buildings are different. They concentrate enormous weight on relatively small footprints, creating point loads that stone columns alone can't handle. For these structures, engineers use deep pile foundations. Piles are long, slender columns, typically made of reinforced concrete or steel, that are driven or drilled deep into the ground until they reach stable soil or bedrock. In Qatar, where bedrock is often 50 to 100 meters below the surface, piles had to be driven to significant depths. Each pile acts like a mini skyscraper in reverse, transferring the weight of the building down through the soft upper layers into stronger strata below. The piles are grouped together under critical load points, building columns, structural cores, heavy equipment rooms. A single terminal building might rest on hundreds of individual piles, all working together to support the structure and prevent settlement. Engineers carefully calculated the required number, diameter, and depth of piles based on soil conditions and building loads. Too few piles, and the building sinks. Too many, and you waste money and time. Computer modelling and geotechnical testing ensured the design was both safe and economical. Building on reclaimed land introduces another challenge: water. The Persian Gulf is right there, just meters away, and groundwater levels are high. Without proper drainage, water would seep into the reclaimed fill, increasing weight, reducing soil strength, and causing ongoing settlement. To manage this, engineers installed extensive drainage systems throughout the site. These include perforated pipes buried beneath the surface, drainage blankets made of gravel, and pumping stations to remove water continuously. The drainage system serves multiple purposes. It prevents waterlogging of the fill material, maintains soil stability, and protects underground structures like utility tunnels and foundations from water damage. In a region where summer temperatures exceed 45 degrees Celsius and evaporation rates are high, managing both surface water and groundwater is critical. Additionally, the airport is designed with surface drainage systems, storm sewers, retention ponds, and outfalls that direct rainwater away from runways and taxiways. Even a few millimeters of standing water on a runway can cause hydroplaning, turning a safe landing into a catastrophe. Once the ground was stabilized, compacted, reinforced, and drained, the actual runway construction could begin. But this isn't like paving a road. Runways must meet incredibly strict tolerances for flatness, slope, and smoothness. Even minor deviations can affect aircraft performance, safety, and passenger comfort. The runway base consists of multiple layers. First, a sub-base layer of compacted gravel provides additional load distribution and drainage. Then, a base layer of crushed stone is placed and compacted to exact specifications. Finally, the surface layer, typically asphalt or concrete, is laid using laser-guided paving machines that ensure millimeter-level precision. For international airports handling heavy aircraft like the Airbus A380 or Boeing 777, the pavement must be thick and strong. Concrete runways can be 40 to 60 centimeters thick, reinforced with steel mesh or fibers to prevent cracking under repeated heavy loads. Engineers also account for thermal expansion. In Qatar's extreme heat, pavement expands during the day and contracts at night. Expansion joints are built into the runway at regular intervals, allowing the pavement to move without cracking. Every meter of runway is surveyed and tested. Profilometers measure surface smoothness. Ground-penetrating radar checks for subsurface defects. Load testing ensures the pavement can handle the weight and impact of landing aircraft. Even after construction is complete, the work isn't over. Reclaimed land continues to settle for years after the initial load is applied. Engineers must monitor the site continuously to detect any movement, settlement, or structural issues before they become dangerous. The airport is equipped with an extensive network of settlement monitoring points, benchmarks embedded in the pavement and structures that are surveyed regularly using precision GPS and laser leveling. If any area shows signs of excessive settlement, engineers can take corrective action, such as injecting grout to stabilize the ground or adjusting drainage systems. Runways are also subject to regular inspections. Cracks, surface deformations, and joint failures are repaired immediately to maintain safety and performance. In a high-traffic airport, even minor pavement damage can escalate quickly if not addressed. Qatar's ocean airport isn't unique in facing these challenges. Around the world, cities are running out of land and coastal areas are turning to land reclamation to accommodate growing populations, expanding infrastructure, and increased air travel. Singapore's Changi Airport was built partly on reclaimed land. Hong Kong International Airport sits entirely on an artificial island. Japan's Kansai International Airport, built on a man-made island in Osaka Bay, has been battling settlement issues for decades, requiring constant monitoring and ground improvement. The techniques used in Qatar, land reclamation, dynamic compaction, stone columns, deep piles, drainage systems, and precision monitoring represent the state-of-the-art in building on unstable ground. But they're also expensive, time-consuming, and require ongoing maintenance. Building an airport on reclaimed land is a gamble. It's expensive, it's risky, it requires decades of monitoring and maintenance. So why do it? The answer is simple: space. Cities like Doha, Singapore, and Hong Kong don't have room to expand inland. Coastal areas are already developed, and land is scarce and expensive. The ocean offers unlimited space, at least in theory, but that space comes with a price. Every square meter of reclaimed land requires tons of dredge material, months of compaction, thousands of stone columns, and continuous monitoring. The engineering is brilliant, but it's also a constant battle against nature. Qatar's ocean airport proves it can be done. The techniques work, the airport operates safely, handling millions of passengers without sinking into the Gulf. But it also proves that building on the ocean isn't easy, isn't cheap, and isn't something you do unless you absolutely have to. And as more cities run out of land, more will face the same question. How far are we willing to go to build on water? Thank you for watching.